page also. All those 5 module slides are already shared long back. So that is the syllabus up to decision tree.
Okay. Okay, ma'am. Yeah.
Yeah.
All good.
Okay, so I also again uploaded slides on Teams, which were already uploaded on the Takshila. So anyone got time to go through it? Yes.
I'm going by your pace basically. So I didn't get the chance to look into that, ma'am. But last classes I have gone through, so pretty much things are clear to me. Yeah.
Okay, okay. 1 minute. Yeah. I was making some last minute changes, and I think I made the changes in the wrong version. Let me just correct it. So yeah, anybody else? You understood, because today again we are going to start a new topic on classification. But if you've already learned, I mean, if you're clear till now, logistic regression will not take much time to understand. Just that it's a classification algorithm. So we'll see some theory of classification first. I'll start, but I'm not saying anybody who has actually gone through the slides.
Yes, ma'am. You can start.
Okay, so regression algorithm, we will only be in our syllabus will only talk about linear regression, but along with the regression we have discussed everything with respect to regression, like regularization, evaluation metrics, etc. The same concept of regularization applies to classification algorithms as well. Equations will slightly change, but the theoretical understanding will not change. Even if you will study tomorrow neural network, the same concept will apply there as well. Bias, variance, everything will remain same. So it's more of a generalized theory rather than specific to any a single algorithm. Algorithmic specific equations might vary, but not the theory. For classification first, we will see some basic theory on decision theory, where you will see a different classification approaches: probabilistic generative models, discriminative models, discriminant functions. These are the 3 major categories of algorithms. Then I'll explain logistic regression, which is a classification algorithm. And then logistic regression is a binary classification algorithm. So in our data set, if there are only 2 classes, we can use logistic regression. If we have to use for a multi-class, that means I have more than 2 classes in my data set, how we can use a logistic regression. So we'll discuss about that. Okay, so here I would like to know whether you have how much you have done in your ISM course. Have you done the concept of probability distributions, joint probability, conditional probability, Bayes theorem? Any of these things are done?
Yes.
Bayes,
Conditional
Bayes,
and
Yes,
Bayes
all
base.
these are
theorem,
done.
Those are all done.
Bayes theorem
Bayes
also done.
theorem, Bayes theorem done,
Yep.
and conditional probability done, joint probability
Good.
also I think done. Yeah.
No, if
No,
conditional is
joint
done, joint
probability
is done.
is not done.
No, no.
Joint
Joint
probability will
probability.
be done today.
Yeah, yeah. So joint probability is not done. In the webinar, they told us like gave us little heads up, but in the class it is not covered. Joint probability.
See, if you know the conditional probability, you will know also the joint probability, because the formulas are related. You might not have done joint probability distribution. Okay, so the formula,
Disjoint probability.
yes.
Joint was not happened, ma'am. Disjoint probability is completed along with
Then
conditional
how did you
probability.
compute conditional probability? This is a formula for the conditional probability. Yes, it involves joint probability divided by marginal probability. So, you should be knowing what is joint probability. You should be knowing what is marginal probability. Then only you can know the conditional probability.
Distribution
Okay,
part
ma'am.
is not done. Other
That is
than
That's
that,
okay.
everything is
Oh, I'm
complete.
only interested in intuitive understanding, no formula, no estimation. We will not do any estimation here. It's just understanding part. Okay. More on detailed probability will come post mid semester. Only to understand this concept of generative models, you need to intuitive understanding of joint probabilities needed. That's all. Not the formula,
Ma'am,
not the estimation.
ma'am, joint probability means you mean that if the two events happening at the same time, like intersection of the two events,
Yes.
I think
Yes.
that has been covered.
It would have been covered. It would have been covered because you cannot learn conditional probability without a joint probability. Distribution is a different thing. Okay. Here you might have learned with respect to events.
Yes, ma'am, that is done.
Yeah. So here just to we'll touch upon this concept of probability distributions here to understand different classes of algorithm classification algorithm. That's all. Now, in case of classification, our target variable we are predicting along with the value of x, and our target variable t is a target variable, is a discrete type, and x has our features. So in this theory, what we'll try to do, we'll try to find out the joint probability distribution of x and t. So this is what probably we'll learn, concept of probability distribution and then concept of joint probability distribution. When you say a probability for one event or probability or one value for random variable or a probability of many values of random variables, then we call it probability distribution. Here we have lot of examples. We are talking about many values. All our examples are one instance of your random variable, or I can say one value of your random variable. So that's the reason we can talk about joint probability. This is what we need to identify. What is the probability that so and so feature exists along with the particular class variable? Okay, I'll explain in detail. Just hang on till I complete this decision theory before you start your questions. Okay, here now our target is discrete. For regression, we discussed about the target variable, which is continuous in nature. Now it is discrete. If it has got more than two classes, like yes, no, maybe, like in this example, which is enjoy sport, which is target variable is enjoy sport, which is discrete in nature. If it has got three values, then we call it multi-class classification problem. If just two values, that's binary classification. And these all are our features. Mute yourself. Mute yourself. So okay, take another example. We have a one feature CGPA, IQ is another feature, and this is normalized feature. Okay, so in data pre-processing, you have done the two normalization techniques. This is normalized feature. So we won't use this X2, but we will use normalized feature. And target value is job offered, which has got only two values, 1 and 0. So this is a problem of binary classification. Instead of this, like what the job offered, that's what we want, either a job offered or not job offered, 1 or 0. We can also, there are classes of algorithm which can give us output in the form of probabilities. So they are known as probability estimations that we are doing. Say very simple example, very simple rule. If our CGPA is say less than or equal to 5, IQ is greater than 7, then what is the probability that a person will be offered a job? Say probability is coming out to be given to, say this is a training data set, so it's given to us as 0.4. Okay, how will we interpret? See, let's say an example. We have a threshold. Okay, if a probability is less than 0.5, we will assign a class 0. If a probability is greater than 0.5, we will assign a class 1. So there are suites of algorithm which will give us output in the terms of a probability, and then we convert those probability values based on the threshold that we choose, whether it's a class 1 or a class 0. Okay, this is a theory of probability. Now, what is this 0.4 probability? It is known as a posterior probability. how, okay, when you try to say trying to understand intuitively, how do you get 0.4? By putting up this, understanding these two rules. I'll check whether for every example, if these two rules satisfies that CGPA is less than 5 or IQ is greater than 7, then the probability is 0.4. That means given the features, what is the class? So I will write down in the form of the probability, given the features, what is a particular class? So I can say, for say this in this example, what is the probability that given class is say 0 given feature X, or what is the probability that class is 1 given the feature X. So this is known as a posterior probability. Probability. We will compute this posterior probability for the unknown examples. So you can say this all posterior probability we have not calculated, it is given to us. But when it comes to a testing, this is unknown example, unseen example. In that case, we will calculate, we have been given only features. So we have been given only features. So based on that, what is a probability that this feature combination that we have observed belong to class 1 or class 0. So that's how you can interpret it. But what is given to us? What is given to us is this: a joint probabilities of features and the corresponding class, because that's what is given in our training data set. In the training data set, we have got the input features and we have got the target variable. And so I can say this is what is given to us. So this is problem of joint probability distribution. If we have been given the joint probability distribution of input features and the class, okay, if that is given to us, we can find out the posterior probability using Bayes theorem. And this is a formula of joint probability distribution, and there's a relation between joint probability distribution and the conditional probability distribution. Now, what is this which is given to us? For each class and for each training example, whether it belongs to class 1 or class 0, what are the combination of features that exist? Now look at this from a different perspective. Say for example, class is 1, whose posterior probability is 0.8, which is given to us. Given this information, what are the specific combinations of the features that we observe? So I'm now changing my my intuitive explanation. Rather than looking at the features, okay, because we have been given everything, features and the training data, in the training data set, features and the target variable both. So let's understand for each example, given that this example belongs to class 1, what are the specific feature values that we are observing? Okay, so now that my statement changes. That is known as a class conditional probability. This is anywhere conditional probability. Given a class is with us. What is the feature values that we are observing? So these are the slides which I've added little extra, which is not there in the uploaded one. So I'll re-upload this on the existing slides which I've uploaded on Teams. So take an example. Suppose we have got two classes of images or two classes of objects, apples and oranges. And we have got a feature set with us: weight, diameter, color, etc. Now, if I want to intuitively understand what is a class conditional probability. So what it tells, class is given to us. That means we have a training data and we are looking at one example. I have 10 apples and 10 oranges. Then I've picked up one apple. So I'm looking at the apple. The class is with me. Given we are looking at an apple, what is the probability of observing this specific combination of weight, diameter, and color? That is what is known as a class conditional probabilities. And in other words, it is also known as a likelihood. Very important concept. when you will learn in your ISM class, try to pay more attention to this likelihood, even maximum likelihood, etc. We will be using this extensively post midsem. Okay, so here just to understand this probabilistic generative model, even if you do not understand in detail, still it's okay. So I can say this class conditional probability is how likely these features are under the assumption of class C1 or class C2. That's the understanding of class conditional probability. I've added one more example so that you understand the difference between these two quantities. Both are conditional probabilities, but in our machine learning term and in our statistical term, this is class conditional probabilities, our machine learning term, and this is posterior probability. I'm only talking about right now class conditional probability. Say another example. We want to identify from the emails whether it's a spam email or non-spam email. And let's say for a simplicity, we have just crafted two features. We have handcrafted just two features. First feature is number of exclamation marks, and another one is presence of word free. Whether free, free word is present in my email or not, like you have got a free discount or a free item, things like that. Say this is what we have observed from our training data, and then we have calculated a probability. Say class C1 is a spam email and X1 is a feature which tells us about the number of exclamation marks. So what it tells, the probability of having 5 exclamation mark in the spam email is 0.6, which is definitely high. Similarly, probabilities of containing a word free in a spam email is say 0.8. That means this class conditional probability is telling us there's a high probability of observing our features which are exclamation marks and a word free in the class C1. The other example, probability of observing this feature combination, that means 5 exclamation mark in class C2 is very low. Similarly, probability of observing a word free, a particular feature combination in a class C2, which is a non-spam class, is 0.1. That means observing this feature combination like 5, x1 equal to 5 and x2 equal to 1. Observing this feature combination for the class C2 is very low. That's the intuitive understanding of class conditional probability. And this conditional probability is related to joint probability. It's just a formula. You can always remember this formula. Either we will find out class conditional probability, or we can easily, once one is given, the other can easily be found out. So interchangeably, many times joint probability distribution or the class conditional probability, that can be used, those words in the same setting. Okay, so now going back to this example, this joint probability distribution is given to us, and we need to calculate this posterior probability based on the joint probability distribution. Obviously, here we are not talking about the training data. When I say I want to find out the posterior probability, that means on the unseen data, testing data, unseen data. We use the Bayes rule. This is a Bayes rule, very powerful rule. There is a lot of theory books on Bayesian learning or the Bayesian understanding, Bayesian reasoning. Okay, so what it tells, the formula is in this format. This is a class conditional probability multiplied by this marginal probability divided by this marginal probability. But here we are talking in terms of our machine learning. We can call this as a likelihood. The second term is our class prior, and this term is our evidence. So what is this? Again, Bayes rule you will learn many times in your ISM also, will learn post mid semester also, but just so that you understand what is this Bayes rule and why it is important. I've added simple definition. So what is this class prior? Example, prior probability of a class CK. We call it prior. It's a technical jargon. And this one is a posterior. So just given one example, our sports enjoy sport class. So suppose I have two classes, enjoy sports or not enjoy. These are my two class values. And how will I interpret this prior? Understand this prior. What does it intuitive understanding? Probability that a person enjoys sport, irrespective of what is a weather condition. So in our enjoy sports example, we have weather condition as our features. If I go back here, 1 minute. Yeah, sky, air temperature, humidity, wind, water, forecast. So all these are our weather conditions. So irrespective of what are the weather condition, a person will always enjoy the sports. What is that probability is known as this class prior probability. Without any data set, without any evidence or a data set available to us, what is the prior? What we know about the domain? So we know about that sports people, athletes will always enjoy playing sports with irrespective of what is the weather. So that's my understanding of a domain of human nature. That's my domain. Now observing a weather condition, whether this class conditional this prior is changing, it might change. So that is what is a posterior probability. That's the relation between a prior and a posterior probability. From a prior, we get certain evidence, we get a data. So based on that, our belief, my belief of a human nature was like this: all sports people will always enjoy playing sports irrespective of a weather condition. That was my belief. It can be refined if I get more data points that I have got certain weather condition and whether person is enjoying sports or not. I've got that data points, that survey, I've got it. So that has changed my belief. So from prior, we have come to the posterior probability. This is what is very basic intuitive understanding of Bayes rule. Why we are talking about here? Because the class of generative algorithms, they actually gives output in the form of this posterior probability. So what is our in machine learning problem setting? What is our aim? To minimize the chance of assigning features to the wrong class. That's what we want to minimize. So we can say that we can pick up a class whose posterior probability is the highest. If I say that a person will still enjoy the sports with so-and-so weather condition combinations. So suppose if I have got something like this, and I have got other probability, other class probability, enjoy sport, not enjoy sport. Okay, so this is C1 and this is C2. So if this posterior probability is greater than the other posterior probability, that means posterior probability of enjoying C1, enjoying sport, given the features, all the feature combination that we have derived from our data set, is greater than a person not enjoying sport for a certain feature combination, then we can say that we can make our decision. Pick up a class whose posterior probability is highest. Now this very basic understanding of the probability we will use to understand the classes of algorithms. The very exact instance where this posterior probability is used actually as for the classification as one of the classification algorithm is a Naive-Bayes algorithm, which is based on the Bayesian theorem, and we'll see later. Here I'm just using this concept to explain you the classes of algorithms, classification algorithms. Going back to our same problem of CGPA, IQ, now we have a job offer like 1 or 0. This is our training data. We can use the learning algorithm. and we are learning a model. That means we are trying to find out the joint probability. What is a accurate joint, I mean not accurate, what I should use the word, what is a correct joint probability distribution for a given feature combination for class 1 and for another set of combination for class 0. Now you can observe over here, say this is class 0. We have got 3 examples which belong to class 0, and we have got a certain feature combinations over here. Similarly, class 1 also we have got a certain feature combination. So that's what we learned. What are the feature combination which belong to class 0 and what are the feature combination which can belong to class 1? Once we learn this from our training data, we call it induction or a induction step or inference step. Once we learn this from a training data, then we calculate the posterior probability and then apply the decision. So our training helps us to calculate the posterior probability based on the joint probability distribution which are given, which are learned from our training data set. Then we make a decision. If we encounter this kind of feature combination, whether a person will be offered a job or not. Now, this decision step is based on the probability, posterior probability that we get from training data. Okay, now I'm just going to talk about decision theory in terms of finding out the error in this term here. Now, suppose this is my hypothesis, very simple rule-based hypothesis function. After the training, this is what I found out. If CGPA is greater than 7, then job offered is 1, else job offered is 0. Okay, from our training data set, this is what I have, our model has learned a hypothesis. Now just understand this and relation between what is drawn below. The first graph is a CGPA on the x-axis, that means my feature. On the second graph is a probability density function for the feature. Now here you can think about a random variable. Every feature is a random variable. Randomly it can have any values. You have learned the concept of random variable in your ISM course. So consider your CGPA. So this is one feature, this is another feature. We can consider every feature as a random variables. So right now for the illustration only, let's take one feature, CGPA. So we have a one random variable, and on y-axis we always plot the probability distribution function of this random variable. That means what are the different values this random variable can take. Now this random variable is my CGPA, and I have got a training data set with us. So based on the training data set, we have to find out, I mean, it's clearly given here that probability of happening 0.5, that our x can get a value of 5.5, then 5, then 8, and so on. So based on this, we get this probability distribution. So do you know what is the concept of probability distribution?
Yes, ma'am.
Okay, so this is clear. Now here, this is a distribution for the class 0, the blue class, the blue color shaded. We have only picked up the values which belongs to class 0. So this, say for example, this 3 values which belong to class 0. Now I'm trying to map it. Where does it belong? Based on the threshold that I have learned from my hypothesis. Say I've learned a threshold of CGPA equal to 7. So I'm just mark this boundary over here, which tells me CGPA greater than 7 is class 1 and CGPA less than 7 is class 0. So this hypothesis is giving me a decision boundary. So what do you see over yellow here is a decision boundary. Very important concept again, decision boundary. Now if I just map the first 0 where CGPA is less than 5. So it will be somewhere in this region where you can see my blue arrow. It will be in a blue arrow. But the other example, class is 0, but the CGPA is greater than 7.5. So it is somewhere here, this portion. Now tell me what I'm trying to say with this. I'm just trying to show you that this 2 training example belongs to which part of my probability distribution for the class 0. What I'm trying to tell over here.
Error you are trying to solve.
Huh? Sorry?
Error.
Error. Correct. So error, right? My hypothesis, because this is what I have found out after from the training data, but still these are the example which actually belong to class 0, but will be misclassified as class 1 as per my decision boundary. So that's what I'm coming to. This is the minimum best rule that I can get. Okay, you can clearly see. Okay, now look at the right hand side. The green shaded curve. That's the probability distribution for the class 1. So what we have done, we have picked up all the examples belong to class 1 and then plotted for only CGPA what all values it can take. So based on that, we have drawn the probability distribution. And then again, I'm plotting this decision boundary over here. It's the same problem. Anything on the right hand side will be correctly classified. So all this point will be correctly classified by our model. But this portion that you see over here, they actually belong to the class 1, but will be misclassified by our decision boundary. So here what I'm trying to show is the misclassification error. These are the minimum misclassification error after getting the best model. Obviously, not necessarily every algorithm will give you the best decision boundary. But suppose this is a best decision boundary, you can clearly visually see from the diagram, this is what we can get best to differentiate between blue class and the green class. Why this is a problem occurring that we cannot get any better than this? Because when you look at this blue and green, blue are the class probability distribution for the class 0 and green is for the class 1. They are overlapping. You can clearly see they are overlapping in nature. So both the class probability distribution are overlapping in nature. That's the reason that the minimum error is bound to happen. And that's where come the concept of minimum misclassification rate. We cannot get rid of it based on our training data. If our training data would be really nice, it can clearly differentiate between class 1 and class 0. Nothing like that. But real world data sets are not like that. So the minimum error is bound to happen during the training. So this is a theoretical basis of errors. Okay, so here X0 is what I showed in the last slide where CGPA is equal to 7, which is also optimal decision boundary. Okay, for this kind of distribution. But we may get a different data set, not exactly a correct data set, which can help you to find out optimal decision boundary. Or sometimes your algorithm chooser is such that it is not giving you the optimal decision boundary. So in that case, see, this is some decision boundary that we have got, some rule. Rather than CGPA greater than 7, CGPA greater than 8. Okay, so the error will further increase. In this example, this red portion, green portion, and the blue portion, these three combinedly represents the error. Now we are interested into the error for both the classes, class C1 and class C0, both the classes. Say C1 and C2 or whatever class number you can give. Class 0 and class 1. For both the classes, this 3 region represents the error. So we can write down. Here we are talking about the region. So we'll take the integration. Before that, what is this? Probability of a mistake. Probability of the error. That the actual point X belongs to class C2, but it is being assigned to region 1. Region 1 is which region? Region 1 is the class region for the class C1. And region 2 is for the class C2. So this says that what is the probability where the actual data point belongs to class C2, this part. But it is being by the model, it is being assigned to the region 1. Region 1 is this side. That means the class C1 is assigned. The vice versa for the other class. The data point belongs to class C1, but it is being assigned to region R2. So you can see this, my arrows over here. The blue region is actually the second term in our equation. This is the error region. Why do I call the blue as error region? Because though all those data points actually belong to the first curve. If you look at this first curve, they actually belong to the first curve. That means they belong to class C1. But due to the decision boundary, they are assigned to class, they are assigned to region R2. That means they are assigned to class C2. Okay, so here we are talking in terms of the region. It is simply written in the form of integration, integrating over the region R1. This is the error term. The class actually belong to C2, but assigned to region R1. And the second error term is a vice versa. A data point belong to C1, class C1, but it is assigned to class C2, that is a region R2. This both combination is known as a probability of a mistake. Okay, so this is what we have derived based on the concept of a probability distributions. First, we started with plotting the probability distribution of, joint probability distribution of features and both the classes separately. And then we have identified what are the error regions. This red, green, blue, they are the error regions. And then we are coming up, this is the mathematical definition of the errors, that is which are there in the red, green and blue region. From this, what we are understanding. So the first integral is what? Probability of misclassifying C2 point as C1. The point belongs to class C2 but assigned to R1. And the vice versa for the second term. That means we want to choose if some new data point is coming. This probability distribution is from the training data set. But if new data set is coming, which will choose a class, which class we will choose? Where the integrand value will be smaller, because these two terms are the error terms. And we have divided error terms into two error terms contributed due to misclassification of both the classes. So we will indirectly choose a class whose joint probability will be higher. This is the error term. I want to choose this as small as possible. That means the probability that X belongs to C1, I should always choose this. When this is higher, I should choose the class C1. That means this error term will be minimized. That probability, actually the class, the data point belong to class C1, but it is assigned to C2. That means we should always choose while making a decision whose joint probability is higher. Now we know this. What is the relation between joint probability and conditional probability? Simple, apply the formula of joint probability. This is a formula. Using our Bayes theorem, we can also use a Bayes theorem. We can also use a conditional probability theorem. So this tells us we should always assign a class whose posterior probability is highest. So I started to show you the relation between a joint probability and a posterior probability, which uses Bayes theorem. So Bayes theorem is what? Why it is called? So if I go back in this Bayes formula, my numerator is nothing but a joint probability between x and ck. So this is a formula I have already mentioned here. Joint probability is what? P of x condition on ck into P of x. So using these three sets of formula, we can say that if I say that I have to pick up a class whose joint probability is the highest, that means I have to pick up a class whose posterior probability is the highest. So that will give us the minimum error. If I always choose a class whose posterior probability is the highest for that given data set, for that model, I will always get a minimum error. So that's the idea why posterior probability is important and why we should choose the highest posterior probability and assign a class based on that highest posterior probability. So for that, this simple concept of decision theory, where we make a decision based on a different thresholds. For a given chosen threshold and a given data set, what is the minimum error that we can achieve? I want to achieve the minimum error. How can I achieve? By choosing this posterior highest class with the highest posterior probability. Obviously, if my threshold is changed from x bar to x0, that means I'm changing the model. The decision boundary is changed. But for that decision boundary, again, the error term will change. The minimum error will change. If I want to compare this two threshold, which one is better threshold? I mean, if I want to compare this two decision boundary, which one is better decision boundary?
We'll compare the
X0.
error.
X0.
X0, because that is minimizing the error. Okay. But within the whatever we have chosen decision boundary, whatever our and how we choose a decision boundary, what model is giving us? The model after training or the training data set will give us a decision boundary, whichever model you are using. Okay, whether it's a decision tree, it's a neural network, whether it is SVM, anything, that decision boundary will decide. So, so the algorithm which will give us output in the term of probabilities, how will you interpret it? For this decision boundary, which has been learned by our model, if I choose this, if I try to maximize the posterior probability, I'll get the minimum error. That's the idea of minimum misclassification rate. We cannot get rid of anything. We cannot reduce it below this due to the nature of our data set. And this is how this diagram will actually tell you this kind of probability distribution that we will actually observe in our real world data sets. Okay, so now if you've got any question, ask me, then I'll just go ahead with the types of classification.
Ma'am, I have two questions. First question, class conditional probability, can we say that is same as reverse probability?
Reverse probability. No. What is reverse probability? I don't know any reverse probability concept.
Okay, so in the ISM, it was told to us like given a particular occurrence of a particular event, like okay, final event, we know probability, and finding out how like the prior event occurred basically, that is known as the reverse probability.
See,
So
here
that's
in
what
machine. Oh, okay. Here we are not talking in terms of events. Okay, here we are talking about distributions and the random variable. So there is here we don't talk any terms of reverse probability. You may okay, you are talking about the absolute understanding of that may be true, but not in
Okay.
terms of our distribution.
Okay, got it. One more question, ma'am. Here in
Huh.
this example, you have considered CGPA is greater than 7. When we have considered, like that is something we have assumed. So
Huh.
when we are considering it 7, the decision boundaries like difference between x0 and x1 is like very high. But when we are considering it maybe, for example, greater than just 5, it will be very less. So this condition which you have assumed right now, this is for the sake of explaining us like
Yes,
what can
yes,
be. Okay, okay.
yes,
Got it.
yes, yes.
Thank you.
Okay, okay, fine. I don't see any question. A book for machine learning and mathematical modeling. Tom Mitchell is good book. Christopher Bishop, that's what we are referring as a textbook. Other than that, there's one book called Statistical Learning. I forgot the author. I mean, I don't remember the author name, but you just search on Google. It's very famous. Its PDF is available. So all of you're not audible. So that statistical learning by there are two books of that author. Okay, then there is another buying is I will not suggest that you buy any book as of now because we have bits and pieces and if you are referring for the syllabus, but for your understanding there is also all of this PDF are available. There's another book, very nice book if you can understand. We are not referring in our as a textbook or a reference book. Probabilistic Machine Learning by Murphy. It has got two parts. So for your basic understanding and you want to have a really clear understanding, you can read that first book. And for the advanced topic like generative AI and for the maths of that, you can understand that's Murphy's second book. It's totally on the probabilistic machine learning. Yeah, please go ahead. Someone wants to ask, Pranav or Shailendra Kumar, any one of you.
Yeah, ma'am. I, I wanted to know the posterior probability you have mentioned, right? So
Sorry,
the example which. Hello, am I audible?
Yeah, yes. What you said, please repeat.
The CK slash X probability. What is that?
Posterior
Posterior
probability. Yes,
Yeah.
yes.
So that one you have mentioned. Can you explain the value of it compared with the CGPA example? Like the
I can spend time on that, but not required right now. We'll again spend time on that post mid semester. You'll again spend time on that in probability. I'll be only repeating what other you will learn in ISM and what we will again do with respect to Naive Bayes algorithm. As I said, this was just
because I didn't get the difference between like X slash CK and CK slash X. What's the difference between those two?
So for that, your probability basics are required. That's the reason I added. I anticipated that this question will come. That's the only reason I've added this here. What is the class conditional probability? I clearly explained this thing. But more time I spend on this, we will lose out on the what is required to be done before mid semester. We are again going to come back to this post mid semester. It's not like that I'm going to leave this. But I just added this because so you have to understand what is a class conditional probability and the posterior probability. They both look so similar. So you will learn in your ISM class. Ask your maths teacher also to elaborate bit on this. Okay.
Hello, ma'am.
Yeah. If not, I'll again come back after. We have two sessions, two modules on the probabilistic machine learning. I'll come back on that. Okay. Yeah.
Hello,
Yeah,
ma'am.
ma'am.
Aman this side.
Sorry. Yeah, please go ahead.
Yeah, so basically, I wants to know why we consider the first decision boundary better than the second decision boundary. If you can tell me through the graph,
Aman.
yeah.
Yes. See, certain things mathematical and visually. This is just a visual understanding. You can think about this visually, you can see. So after the class, spend some time on this. You have to look at the graph and understand. Okay.
Yeah, but just give me an overview, why we
I've
are
given
coming
already
to this.
overview. Aman, I've already given overview.
Yeah, I want to know again. Can you please explain again?
Can I request you, can you go back to the recording after the class and you can mail me, ping me on 1-to-1 if you don't understand still? Can we follow
Okay.
this for every class? You can ping me
Okay.
on 1-to-1 email. Okay, go back to my recording again. Once, twice a month for specifically for you. If you do not understand, just email me on 1-to-1. We can connect on any of the weekdays and we can connect.
Okay.
Okay, you can ping me, you can email me. Because for one, what is happening, the entire class is getting delayed. Yeah, if that's a general question for everyone, I'll take up. For any specific question anyone have not understood, please ping me, please email me on 1-to-1. We can connect any of the weekdays. Yes, anybody? Anything else?
Just one more,
Yeah,
like
yeah.
no, general question from my side. Like here
Mm.
on all of the topics, we have written a decision theory. Like how it
Yes.
is a decision theory. That is what not
Huh.
I'm getting.
Okay, yeah, that's what I was about to explain the next. See, we have used this decision theory here. With respect to the decision boundary, we are changing the decision. Okay. And with respect to the decision boundary, we have come up with this equations. That's a mathematical modeling of a decision. So we are using, why we are using this? During our inference stage. Okay, we have a training stage, then we have an inference stage. We are getting this probability, posterior probability we are getting. And based on this posterior probability, we are making a decision for the class assignment. And that's how the decision theory comes into picture. This decision theory is telling us choose a class which posterior probability is the highest. So when you will see the classes of algorithm, which gives output in terms of a probability, but not 1 and 0. So how do we say that so and so probability is the class 0 and so probability is class 1? Because you can choose, first of all, which class I should choose. For every example, I have got two probabilities for the class 1, for the class 0, 1 for the class 1. Two posterior probability will get for every example. Why I'm choosing the maximum posterior probability for the positive class? So that justification lies over here. And for that, we started our assumption, our understanding of probability distribution and the decision theory comes over here that this mathematical modeling is from the decision theory, which uses these bases of our decision boundary. So whatever decision boundary we have, so based on that, we have two sets of error. One for the class C1, one for the class C2. So that's where the decision boundary is coming here. Have I answered your question?
Yes. Thank you.
Yeah, so we use that decision theory because we are taking a class which posterior probability is the highest. And because of that, we are making a decision for a positive class or choose a class whose posterior probability is the highest. Suppose I have a spam email and non-spam email. 1 minute, let me complete. So I have a two class spam and non-spam. If I take, suppose I have this two posterior probability, this is 0.5. Sorry, say this is 0.6 and say this is 0.4. Which one I'll pick based on a decision theory? I'll pick
0.6.
spam. Spam. Why so? For that justification, theoretical justification was that I was explaining till now, and it's based on the decision boundary concept. And then we have done the mathematical modeling of the decision boundary. Because now we will see algorithms which directly can give us this probability. And why are we choosing that, 0.6 will be, say, for this example, the class will be spam. So that theory lies on this decision theory. Why we should choose the probability which is the highest probability as a class. Okay. Anyone else wanted to ask something?
Yes, ma'am. So class means like a function.
Class, no, CK, class, spam and not spam. That's a class.
Okay, like classification.
Classification.
Yeah.
Okay,
Spam is
okay.
maybe spam is you say 1. Maybe this you can encode as a 0, whatever way you want to encode this. It's a binary class. We are
Okay,
talking about
okay.
classification.
Okay, ma'am.
I'm not
And
gone to the
the book-
hypothesis function yet. Okay, I'm only talking about classification.
Okay, ma'am. And the book names we have mentioned in the chat, can you confirm? I mean, not now, later also, ma'am. Thank you.
Yeah, okay, let me see at the end. Yeah. Okay. So now we are talking about a
no.
class of, yeah, please.
While training, the model is learning uh, mm, that like while training using the training data, it learns
Hmm.
that whatever the features are there, and given it belongs to some group, that is what it learns, right? Belongs to certain class, and from there it kind of extracts a decision boundary, and that decision boundary is used in the classification. In the kind of like once training is done, I want to understand that during using it on testing data, we do not calculate any probability at that time. We use the decision boundary to calculate, do the classification. That is what we do, or in the
No. This is
principle.
a general, okay, this is a general theory I'm explaining. Now there are different algorithm, they behaves in a different way. There are certain class of algorithm which calculates the decision, which calculates the posterior probability. And there are explicitly using a Bayes theorem, and there are certain algorithms which gives us the decision boundary directly. That's what I will explain. Okay, for a logistic regression, that's where I'm going. Okay, now let me complete this first. So we have different class of classification algorithm. Two, generative and discriminative, which are based on the probabilistic models. And discriminant function is a non-probabilistic model. Now, if I just want to another way look at this classification, generative models where we actually find out this likelihood, there is a class conditional probability, then we find out the posterior probability, sorry, I mean a class prior from our data set. Then I have here class conditional probabilities from our data set. Using this too, I find the posterior probability. So Naive-Bayes Gaussian mixture model, they are the class of generative models. Then we have a discriminative models. We still get an output in terms of a posterior probability directly without using Bayes theorem. Those classes of algorithm are known as, they come under neural network logistic regression. They are all discriminative models. Even SVM, perceptron, decision tree, they are also known as a discriminative model because we get a decision boundary directly without calculating this prior and class conditional probability. And in case of a discriminant function, there is no probability. We do not get output in terms of a probability. So SVM, perceptron, decision tree, they all are discriminative model, but of the class discriminant functions. These are the names given, and these are non-probabilistic in nature. Logistic regression is a probabilistic machine learning algorithm, but it comes under the class of discriminative, not the generative. More example, say what is a generative model? So if you use a generative model, which is using, say, Bayes theorem, which uses a Bayes theorem, one of the generative algorithm is a Bayes theorem. So in that we calculate the posterior probability explicitly based on, first we have to calculate this likelihood, which is a class conditional probability. Then we have to calculate the class prior probability from the data set. So we will calculate this joint probabilities when I have all the values. So how does it look like? I will find out the probability distribution for the, say this is class 0. So I can say class 0. Okay, I'll write down here X and class 0. And this is a joint probability of say X in class 1. So we find this joint probability distribution based on the training data, and then suppose a new data point is coming here. What will I classify it as, 1 or 0?
1.
1. If new data point is coming here, what will it be classified as? 0. So that is what is the generative models. The other advantage of generative models, it can generate the data points. I have got only 8 data points, and based on that, I have learned the input data distribution. Can I generate few more data points? All of this, if I generate any data point which belongs to this region, I can always put it as a class 1 region. Correct? Yes. Similarly,
Yes,
if I put anything over here, if I just try to pick up any data points from here, that will belong to class 0. So this is what is the basings of generative models, because we are trying to learn the underlying joint distribution of our data, which is nothing but P of X comma CK, like in this example for a classification example. And if we learn this joint distribution, we get some region. So based on that region, we can generate many more synthetic data, and that's why it's called as this classes of algorithm for a classification task known as a generative algorithms. This is a very quite, like, when maybe if you will learn something about generative models, basic theory remains same. These are the generative models. So what you see Gen AI, which is taken very popular today, it's the same concept. We are learning the underlying data distribution from our training data, and based on that, it can generate the samples. Here it can generate the samples, like our goal is not to generate the samples. Our goal is just to classify the given new sample. We will just find out the new sample belong to which region, whether blue region or a pink region. Based on that, we will classify it. That's our goal. Okay, so all those Gaussian mixture model, mixture of multinomial naive-Bayes Bayesian networks, they all are generative algorithms. That means we have to identify first this joint probability. Then we have to identify class prior. And then we will find out the posterior probability, and based on that, we'll make the decision. We will study naive-Bayes in detail. It will be more clear how practically we are going to do this, compared to another sets of algorithm which will only learn this decision boundary. Now you understood the importance of decision boundaries. One side is one class, other side is other class. So how are we learning decision boundary? In the previous example, I simply taken the, by looking at, okay, I can give, this is if then else rule. That is also one kind of hypothesis. If CGPA is 7, that we have taken, our model has learned, assuming our model has learned this thing. But there are different algorithms which can actually give us, or I can say there are different mathematical functions which can give us this kind of decision boundary. If then else is one kind of a mathematical function, it comes under logical function category. But there are mathematical functions which can give us this kind of a decision boundary by giving us directly this posterior probability. We are not using any Bayes rule over here. The function, there's a different mathematical function rather than a Bayes theorem is used to infer this posterior probability. Based on that, we can get this kind of decision boundary. So logistic regression, neural network, nearest neighbor, they all come under this category of discriminative algorithm. Not nearest neighbor. Okay. It doesn't give us any probabilities, not nearest neighbor. Neural network, logistic regression are part of discriminative algorithms. So let's take an example of cat and dog. Suppose I want to classify between cat and dog, object, image, anything. So what is a generative algorithm? Look at the cat, look at the dog, and learn how they look like. Okay. And based on that, if we can build a model, how the cat will look like, how the dog will look like. So any new image is coming, we can identify it's a cat or it's a dog. So that is what is a generative strategy. like with respect to spam email. Look at what spam email will look like. Look at what non-spam email will look like. And then the new email comes, we can identify whether it's spam or non-spam. Compared to the discriminative, where we will learn certain rules. So based on those rules, we can say if these rules are satisfied, then it's a spam email. If these rules are not satisfied, then it is the non-spam email. That's a discriminative algorithm. Just intuitive understanding difference between. So graphically, you can just remember if an algorithm gives us a decision boundary, rather than giving us the probability distributions, then it is a discriminative model. If the algorithm is giving us the probability distribution, then it is the generative model. Discriminative and generative difference. So another example over here. See, we have images of rabbit and parrot or anything, class 0, or here the image of class 0 and class 1. Discriminative model will directly find the decision boundary. That is a kind of a threshold. And generative model will find out some kind of a probability distribution. And based on that, we can identify if your example belongs to this group, then it's a class 0. If they belong to this group, then it is class 1. So I have given another example, how the cat or robin or any other animal look like, how the sparrow will look like, and then compare both of them. Or learn the rules which can clearly distinguish between two classes. That's a discriminative algorithm. So decision tree comes under discriminative algorithm where we learn the rules. Just intuitive understanding. And the third category is a discriminant function, which also comes under, like in the first class, discriminative algorithm. That means it gives us a decision boundary. So it is still this kind of a nature. It can give us a decision boundary, but its output is not in terms of a probability. There is no role of probability. I mean, probability doesn't play any role over here. No access to posterior probability, nothing. We directly get a decision boundary. So there are class of mathematical functions which can give us a decision boundary without probability. Like SVM, decision tree, perceptron, nearest neighbor, they all are types of discriminant function. And with every algorithm, there are parameters. Like linear regression, we have a parameter like weights. How do we learn? So least square, Fisher's linear discriminant, perceptron algorithm, cross entropy, perceptron algorithm, not the cross entropy. All of this are the technique that we can use to find out the parameter values. One very simple example given, what is a linear discriminant function? This is a linear discriminant function. You can say it's a linear in parameters, simple W0 plus W transpose X. This is nothing but your equation for the linear regression. But here I'm talking about classification. So I will not call it as a linear regression, but it's a linear discriminant function. And then we use this rule. Simple threshold. If a function value greater than or equal to 0, it's positive class. Otherwise, it is a negative class. Mathematically, this rule is written as a sine function. So what I said, there are mathematical functions which can give us this kind of a decision boundary. So sine function is one function which only picks up a positive sign or a negative sign. So for a positive sign, it is +1. For a negative sign, it is -1. Just to give an example, that there are classes of mathematical function which can give me a decision boundary. You will be learning SVM and decision tree, perceptron, not in this syllabus, but we will also talk about nearest neighbor. Okay, so last comparison, a very kind of a summary. For a generative approach, ultimately we have to make a decision whether it's class 1 or class 0. So first we will get this likelihood for both the classes. Based on the likelihood, we will find the posterior probabilities using Bayes' theorem. And then we'll make a decision. The highest posterior probability will take that as the class for that training example. The next approach is discriminative approach. Still, it's a probabilistic approach. We will get this posterior probability directly. We'll use a mathematical function which will give us this directly, and then we make a decision. Pick the highest posterior probability in both the cases. Pick the highest posterior probability. And the third is a discriminant function which directly gives us a decision. No, it doesn't give output in terms of probability. Okay, so for a discriminant function, SVM, perceptron, all of this are. And even if you do not understand, maybe we can come back to this table later. When we'll finish all of this algorithm, go back and see this table, whether it makes sense or not. Okay, right now we'll not spend time on understanding, but I've added this slide just so that you can understand the differences at the end. Once you have learned at least one algorithm, like we will learn decision tree and logistic regression. After that, you can come back and see this, whether it is making any sense or not. Okay, so now any doubt before I go ahead? I'll start with the logistic regression.
Just a generic question
Yeah.
from my side, ma'am. When we say like the SVM and others are non-probabilistic, basically, what actually does it mean? Like they doesn't rely on the probability to
Yes,
calculate it?
yes. Output is not in the form of a probability.
Ma'am,
Decision
just
tree, when you will learn,
if
one
else
minute,
is,
1 minute. You are answering? That's what I was about to say.
you know, I was just asking, the if else will come under that function, right?
Yes. Decision trees, identically, you can think about if else, if then else. So that's a kind of discriminant function. Output is not in form of a probability. Okay, let's do one algorithm, then it will be clear. Logistic
Ma'am,
regression.
I have
Yeah.
one question. So right now we have just considered two classes. That is the reason we have always form a one decision boundary. But is
Yes.
it there could be a case where we have more than two classes classification? How
Yes.
do we do that?
That you will learn as per the algorithm. This is a generic theory, so I cannot answer that question right now. But with the logistic regression only, I'll explain how we can do multi-class classification. That varies from algorithm to algorithm, or the function that we use. It's not a general theoretical question. You will come to know that. Okay. Now, say we are talking about a classification. Can we take the least square regression as the algorithm and do the classification? So say, for example, if I took this linear discriminant function, okay, and I take this linear discriminant function and then make a rule. So say this is a line, my regression line. I will not use the word regression line because it's not a regression problem. This is a line for our linear discriminant function. We are just trying to show that if we use the regression algorithm, which you have learned as a classification for the classification. So for this line is known as a linear discriminant function. And then I use a decision rule that left side is +1, right side is -1. Okay. So mathematically, we can write this as a sine function. This is giving us this linear boundary, this equation of a line, which we are finding out by this equation. It's a linear boundary. It's a line. It's a linear boundary. It's a hyperplane, and this is a rule. So based on this rule, all on the left side, this all belong to class 1, and anything on the right side all belongs to class -1. But our original data set is this. So, oh, sorry. This is a line. This is my threshold line, and this is a line for, say, our this line W0 plus W transpose X. I can say this is a line for this linear discriminant function over here, not this line. This is my threshold line. Based on this line, we are coming up with this threshold, and which will divide our data set into two classes. But the error is bound to happen. Maybe for this data set, we have got this very clear decision boundary and this line. For example, I will use a logistic regression as one algorithm. That's what we will learn, and least square regression. So both of them is giving us this line. Green line is for logistic regression and the purple line is for the least square regression. That is a linear regression using a least square method. For a certain class of our data sets, we have got like this line with the mathematical function, whatever is a hypothesis function. For least square regression, we have got a purple line. And whatever is a hypothesis function for logistic regression, we got a green line. For this data set, they are coinciding and both of them is classifying my red cross and the blue correctly. Like even this example also, I'm getting a correct classification. I can use this linear function and then I can use the thresholding function or the sign function. But what if I add some more data points? They are the outliers. You know the linear regression. By addition of outlier, the equation of a line changes, correct? The best fit model will change. The linear regression is very susceptible or very sensitive to outliers. So my line is changing. My least square regression line is changing. But by addition of this outlier, my logistic regression line will not change. There is a mathematical basis for this, but just a theoretical, this will not change. That shows this. If we use the least square regression for the classification task, we will not get the optimal decision boundary. And here I've simplicity mentioned what is a least square regression. This is what is least square regression or a linear discriminant function. And then we have this a decision rule. We find a line using a linear regression and then we make a decision rule. So we get this a decision boundary, but it is prone to outlier. So now we will see a logistic regression, how it can help to solve this problem. It still uses a linear discriminant function, but rather than using this sign function, like now I'm going back over here. This is a linear discriminant function, and then I'm using a sign function. This
linear regression can also have outliers, no? So
Yes,
outliers can
yes.
have in both the conditions, like both the cases.
It can have. No, I
So
didn't get you.
how come outliers come in the picture? Like how outliers help us in identifying why logistic regression is better than least square?
No, okay. So what it tells, we have after this, we have added few extra data points. Okay, which are this outliers. If I'm adding this extra data points, this line will change. But the logistic regression line is not changing due to its mathematical property. Okay, that we will see the mathematical property that we'll see. So what are we doing? We are using a linear discriminant function or a linear regression function, and then we are taking a sign function to get a decision boundary, correct? That's what we have done here. Use it rather than a sign function. This is a sign function. We will use something called a sigmoid function. Then it will become a logistic regression.
Ma'am, the sine function, is it same as the trigonometry sine cos theta, or this is different?
No, sine, SIGN sine, it's mentioned, no, spelling is also mentioned. It is SIGN. It's a simple sign, positive sign, negative sign.
Okay.
It's a sign function. So if the value is positive, output will be positive one. If the value is negative, output will be negative one. It's a sign function. So this relation mathematically can be written as a sign function. Okay, it's not a sine cosine, it's a sign, positive and negative sign.
Okay.
So now I'm replacing that sign function with the sigmoid function. Okay, this is a definition of a sigmoid function, 1 upon 1 plus e raised to minus a. Now here, what is our a? Z is nothing but W transpose X plus W0. So this is our linear discriminant function. This is exactly a hypothesis function for the linear regression. So we are passing that function to a sigmoid function. This is a symbol of a sigmoid function. So if I just write down a final equation that will look like 1 upon 1 plus e raised to minus W transpose X plus W0. This will become the hypothesis function. This is equal to the hypothesis function of a logistic regression. So the nature of the sigmoid function, it's a S-shaped function. Whatever is input, Z is equal to W transpose X is our input. What is the W transpose X? It's a weighted linear combination of all the inputs. Sorry, weighted linear summation of all the inputs by the linear regression that you know. This is exactly what we do in linear regression, but that we are passing through a sigmoid, which is also known as squashing function, which is a S-shaped function. So what it does, the output. So this is input, which goes to a sigmoid, input to sigmoid, okay, not the actual input. And this is the output of a sigmoid, which will do what do you observe in this S curve? Input range is say minus infinity to plus infinity. What is the output
Means
range?
every value is squashed between 0 and 1, like
Every
under 0
value
and 1.
is correct. Every value is squished between 0 and 1. So any value between 0 and 1, we can interpret it as a probability. So we got this a discriminative model. It's a probabilistic discriminative model, discriminative classifier, and it can also be used for a gradient based learning of the parameter. So we will use the gradient descent to learn the parameters. We'll see all the detail in all the things in detail. Okay, that's the thing. Why it is called logistic regression, though it's a classification algorithm. Why it's called a logistic? Because a sigmoid function is the family of logistic functions. There are more logistic functions like 10H and so on. Out of this logistic mathematical family of functions, the sigmoid function we are using, hence the family is logistic. That's why logistic. And why regression? Because it combines the weight vector. The inside equation is what? It's a regression equation. That's why its name is a logistic regression. By applying, passing a regression equation to the sigmoid function gives us a perfect good decision boundary. Now G is a general symbol. Many times you will see it's a general symbol to denote a non-linear function. But the symbol for the sigmoid is this sigmoid. And can I say it's a non-linear function? You can see it's a S-shaped curve. So function is not a linear. It's a non-linear function. Okay. Now, how do we interpret in terms of hypothesis and a probability, the relationship between a probabilistic output and a hypothesis function? So we'll start with this. The hypothesis function of a linear regression is this sigmoid function. Okay, I can interchangeably write this as sigmoid of W transpose X, where the sigmoid is this function and the Z is this. So I can also write this 1 upon 1 plus e raised to minus W transpose X. This becomes the hypothesis function for my logistic regression. It gives output in the between 0 and 1. That means we are getting output in terms of a probability. So what is interpretation for this hypothesis function? This function I can interpret as a probability of a class 1 given input features and the parameters. So this is condition given in a probabilistic language. We can call it condition. The probability of a class 1 condition on input features and the parameters. That is what is my hypothesis function. And probability of a class 0, again condition on input features and the parameters, equal to 1 minus hypothesis function. This is a relationship between our probability, posterior probability, and the hypothesis function. So negative class probability, negative class posterior probability is equal to 1 minus hypothesis function, but a positive class posterior probability becomes the hypothesis function for a logistic regression, which is this function, sigmoid function. Now about a decision boundary. You have to learn about a decision boundary carefully over here. How we can use, because output will not be in terms of 0 and 1. As you can see, this output is any number between 0 and 1, not just 0 and 1. We want our class either to be 0, either to be 1. So we have to come up with a decision boundary. Now you can clearly see here, say, suppose we come up with this. Our hypothesis function gives us any value greater than or equal to 0.5. This is what is a general threshold taken, because at this point, our sigmoid function changes its direction from a negative to the positive. So for the input space, so this is a threshold you consider here. Any value above, output value above 0.5 will be considered as a class 1. All of this will be considered as a class 1. And all of these values will be considered as a class 0. So when I say, let me complete 1 minute. 1 minute. So when I say this 1 upon 1 plus e raised to w minus w transpose x is greater than equal to 0.5, which will essentially results, which can only happen because it's an exponential operation e raised to something when w transpose x is greater than equal to 0. Okay, because there's a minus over here. If this is a positive number, then I'll get this entire equation. You can just try, take an Excel, take some values, and this will always, for every positive number. Sorry, this is W transpose X. For this positive number, we'll get this entire equation value greater than equal to 0.5. And for a class 0, I need to have this 1 upon 1 plus e raised to minus W transpose X less than 0.5. For the class 0, this will be resulting into our W transpose X less than equal to 0. So I will call this W transpose X equal to Z, just another symbol for our simplicity. And we can easily write 1 upon 1 plus e raised to minus Z, where Z is equal to W transpose X. So our decision boundary, when the linear equation is a positive, 0 or positive, the class is 1. If this is less than 0, the class is 0. This is because we are taking the threshold for the logistic regression as a 0.5. Okay, so indirectly, our decision boundary, I can say, is determined by this equation, which will involve only our input and the parameters. Only our input and parameters is giving us a decision boundary for the logistic regression, and this, because this equation decides the decision boundary, can I say this is a linear equation? It's a linear function, right? Is it a linear function?
Yes.
That is the reason we call it a logistic regression is a generalized linear model. It is not known as a non-linear model. Although we are using this sigmoid function, which is a non-linear, the function, hypothesis function is non-linear, but our decision boundary is based on this equation, W transpose X, which is a linear equation. This is a linear model. It can model only linear data set. It can only give us a linear decision boundary. If I have a non-linear relationship, it cannot be modeled using a logistic regression. Yes. Now you are asking any question?
So, ma'am, the decision boundary is always at half, or like based upon the use case, we can tune it to a higher value or lower value?
No, here for logistic regression, it is 0.5. because of this S-shaped curve. I mean, it is exactly changes its direction at 0.5.
Okay.
Probability
y-
of both the classes you have calculated like 1 minus probability of another class 1 basically. So can we
Yeah.
assume like that is because both the classes are mutually exclusive and exhaustive? Like
Oh, obviously, if one belongs to one class, the example cannot belong to other class. That is assumption.
okay,
Yeah, we
okay.
have a clear
And
decision boundary.
okay, and 0.5 we have assumed here, or like for this particular, it will be always 0.5.
It is 0.5 for logistic regression. Yes, it is
Okay.
0.5.
Ma'am, one query. You mentioned in the last few minutes, you mentioned that we can only have decision defined when data are kind of linearly they have linear relationship. Non-linear relationship, we will not get a good result. But like this is in some sense kind of whatever sigmoidal function you are using, you are kind of using as a basis function that we have seen in linear
No,
regression.
no. Sigmoidal is not a basis function. Okay. Our decision boundaries is based on this linear function. We can use a basis function. But here, sigmoidal is not a basis function. So here, suppose if I, rather than this, if I make like this, I can cater to non-linear boundaries, right?
Yeah.
That's all. But sigmoidal is not a basis function. Okay. Basis function. Can you mute yourself? You have a lot of background noise. So this one is a linear equation. That's why it's a linear model. But I can change it. I can use it for the non-linear data set by changing x to 5 of x. So that linear basis model, all the theory applies here as well. But what sigmoid over here you are using is not for, we are not replacing x by 5 of x by a sigmoid function. We are passing this entire W transpose x to a sigmoid function. See what I taught in the linear basis function, where for the x to 5 of x transformation, I can use a sigmoidal function. That's a different definition, a little bit different definition we have used. But here I'm passing this entire W transpose x, passing through another non-linear function. That's all I'm doing it. So where you are placing a sigmoid function, based on that, whether it's a basis or not basis. Here it's not a basis function. Okay, now, so how will interpret this output? Say we have just one tumor size. Based on the tumor size, whether a person is having cancer or not, or a tumor is malignant or benign. Okay, so say this is my feature, this is a bias term, and this is a feature bias coefficient, and this is the feature. Based on we have done this hypothesis calculation, I've got the output in terms of 0.7. So what the class will be assigned as a 1, because threshold is 0.5. And how will I interpret? This is giving us one more step ahead. We can say this class 1 with a 70% chance. So we can also say how confident we are with a 70% probability that tumor is malignant. That's additional information we get from a probability. Okay, now see decision boundary for a logistic regression. This is a decision boundary where W transpose X is greater than or equal to 0. That becomes our decision boundary. So let's take an example. Here we have two features, x1 and x2, x1 on x-axis, x2 on y-axis. And see, we have got the values of W0, W1, W2 like this. Okay, and this is my sigmoid function. But our decision boundary will be determined by this linear equation. So I'm only interested in this linear equation y equal to 1 if this linear equation is greater than or equal to 0. So I've substituted all these values W0, W1, W2, and I've got this equation x1 plus x2 is greater than or equal to 3. It's a simple mathematics. If equal to y equal to 1, and if this is less than 0, then y equal to 0. So I can say x1 plus x2 equal to 3 is our decision boundary. I'm just trying to show you how you can do it visually. So here I can draw the line, this line, which is the line for x1 plus x2 equal to 3. This is also line for a W transpose X equal to 0. And this will give us a decision boundary. Clear with this?
Yes.
Now suppose if I change X rather than basis function, and I can have some polynomial equation, then I can get a non-linear data set. Say, for example, this is a polynomial equation, and this equation only determines my decision boundary. We have got all our parameter values, and by substituting that, this is what I will get. So this will be reduced to x1 square plus x2 square greater than equal to plus 1. Okay, that means my decision boundary will be x1 square plus x2 square equal to 1. Just substitute these values over here. You will get this simplified equation. Now, can somebody tell me this is equation for what?
Circle.
Circle. So this is the equation for the circle. Again, you have to go to the mathematics and understand the different equation of circle. Likewise, we have a equation of parabola and so on. Okay, this is the equation of a circle. Likewise, we have equation of a line, y equal to mx plus h. Likewise, is equation of a circle. So end passing through all the the radius of 1. That means we will get a decision boundary which is passing through this points 1, minus 1, 1 and minus 1. By changing this linear function to the basis function, polynomial function, we got a non-linear decision boundary. We get a complex basis function, complex polynomial. We can get any complex looking function, non-linear function. So that way we can use the basis function concept here as well, which will help us to cater any kind of a non-linear decision boundary. But logistic regression cannot cater to non-linear data set. So this is a decision boundary for the logistic regression. Okay, so what we have learned till now, we have been given training data set as usual. These are the training M example. And then we have got N features. This is our hypothesis function for a logistic regression. What is a variable? Now we have to learn the parameters. We have to learn this weights. So let's go back. Now we will talk in terms of a cost function. So you remember the cost function, the intuition of cost function. Why do we need a cost function, etc.? Yes.
Yes. Mean square error.
Yes. Yes. So let's take that linear regression. This is a mean square error, linear regression. What happens if we use the same cost function for logistic regression? Okay. What happens? For a linear regression, what is our hypothesis function for the linear regression? W transpose X, correct? And because of that, we are getting this very perfect convex function. So we can use gradient descent algorithm. Now, if I use the same cost function for the logistic regression, it is 1 plus, okay, what is this hypothesis function here? For a logistic regression, it is 1 upon 1 plus e raised to minus W transpose X. Hypothesis function is a non-linear function. So if I use this cost function, I will not get a convex error surface. I'll get something like this non-convex error surface due to the non-linearity in this equation. Our linear regression hypothesis function itself is a linear function. But our logistic regression hypothesis function is a non-linear function. It is the sigmoid function, which is a non-linear. So in our mean square error, this non-linearity will make our error surfaces non-convex. So we cannot use a gradient descent algorithm. So we will use another cost function, known as a cross entropy cost function rather than mean square error. So what it tells, for a positive class, I will use this cost function minus log h of theta x. For a negative class, I will use minus log 1 minus h of theta x. Okay, so this is a cross entropy cost function. There is also theory White's entropy, White's cross entropy. We will not go in the detail of this. Anybody interested? You can just find out what is this, but it's not required to understand a logistic regression function. So understand how will what is required over here, how this cost function will give us a convex error function so that we can use a gradient descent. That's the objective over here. So let's take for the y equal to 1 class. See, this is my function, and this, it's a logarithmic curve. It's a minus logarithm and some value inside. H of theta s is a some value which is 1 upon 1 plus e raised to minus z. Okay, so this is a logarithmic curve. Normally, this is a shape of a logarithmic curve. Here I have a input. Input is our h of theta x and the cost. Suppose if I take a log value, so let me put it, this is minus log of h of theta x, which is on the y-axis. And this will become the curve. Now just interpret this curve. Okay. When the actual value is y. Okay, so this actual value is y1. And the predicted value is also 1. On the x-axis, we have the predicted value. The actual is 1, predicted is 1. What is the cost coming out to be? Yes? 0. If the predicted value is very low, like near to 0 or say 0. It's 0, almost 0, but actually still 1, what will become the cost? It will become very high. So this is what cost is 0. If the actual is 1 and predicted is also 1. But the cost increases if the predicted h of theta x is nothing but a predicted. This is y hat. Oh, sorry. This is not y hat. This is y hat. I use generally y hat to denote the prediction. So if the predicted value is 0 over here, you can see if it is 0, the cost will increase to infinity. So that's what intuition is when the actual class value is 1. Now I'll look at this second part of this equation. If the actual class value is 0. So here I'll look at the second part. So the actual value is 0. And let's see what happens to our cost when our predicted is varying between 0 and 1. So when the predicted is also almost 0 and the actual is also 0, the cost is coming out to be 0. If actual is 0, predicted is also 0, the cost is 0. And if predicted is coming out to be 1, but the actual is 0, in this case, cost will tend to infinity. So this is a desired behavior. Now we'll combine this two. We cannot use gradient descent with this kind of a writing. I'll combine for these two classes and we'll come up with this one equation where I'm combining for the class 1 and class 0. We'll come with this. So this become the cost of the logistic regression. It is the actual value into log of predicted value plus 1 minus actual value into log of 1 minus predicted value. This is the cost entropy function. So what we have done, we have we have combined this both the classes curve, and we are exactly getting our cost surface for both the classes as the convex function. And due to this, we can use the gradient descent algorithm for the parameter finding. So if I just try to write down, and this 1 by m term is, we are averaging the cost over all the training examples. So you can remember the logistic regression cost function 1 by m multiplied by we have summation I is equal to 1 to m. So we are going through iterating through all the training example y into log of y hat plus 1 minus y into log of 1 minus y hat. Very shortened notation to remember. I'm just writing this for a remembering purpose because getting rid of this superscript etc. Y log of y hat plus 1 minus y log of 1 minus y hat. Suppose if I have just one training example, say one training example, then I will simply write this y log of y hat plus 1 minus y into log of 1 minus y hat. And when we iterate over the training example, we'll get this summation sign, we'll get all of this superscript I to denote its ith example, and then we will have to take an average. Okay, this is minus. So this become the cost function for the logistic regression. As usual, we want to minimize the cost function. We can use a gradient descent algorithm, and that means our gradient update rule. Will become new parameter value equal to old parameter value minus this is the learning rate multiplied by partial derivative of our cost function. The only difference of a cost function is not mean square error, but cross entropy function. That's the only difference. Our gradient descent understanding will remain same. What will change? Yes, what will change? That's just looking at mathematics. What will change? We'll not go in the derivation of detail. I'll directly give you the final equations. Derivation not needed. But for your intuitive understanding, tell me what will change in this gradient update. If we have a same equation for the logistic regression and linear regression, we cannot have that same, right? So what will change here? This is the same equation
Cost
gradient
function.
descent. Cost function is changing. Why cost function is changing?
Now it is logarithmic cost function.
Yes, it's a log likelihood, sometimes known as a, but don't go into that detail. It's a cross entropy cross function that will change. Okay. So again, you have to have a derivation like for mean square error, we had a derivative. You have to remember derivative formula and find the derivation of this with respect to every parameter. What it turns out to be, if you see the derivation, it is there at the end of the slide for your self-learning, not required for the to go into that mathematical depth. It is turned out to be both this equation, that is gradient descent update rule for the linear regression and logistic regression, will be exactly same. Okay, this derivation I had shown in the last class because it is simpler derivation. This is a complex derivation, but both of them is resulting into the same thing, like derivative of j of theta with respect to theta is coming out to be same, which is nothing but prediction minus actual multiplied by that feature value. We'll go through, we'll do this for all the example, take the average and learning rate, and this will remain as it is. But still, what is changing even in this also now? My gradient update rule it's the same in both the cases, linear and logistic regression. What is changing? What is different? This hypothesis function is different. For linear regression, it is theta
Sigmoid.
transpose x. For logistic regression, it is 1 upon, it's a sigmoid function. It is 1 upon 1 plus e raised to minus theta transpose x. This is what is changing. So if you've understood the entire theory of gradient descent and then cost function, everything will hold true. The same thing over here, even if you will learn neural network, the theory will not change. There still gradient descent can be used.
Ma'am, I have a question.
Yeah. Huh.
that the cost function will be a convex curve, but it will be a full convex curve because that is a log function.
It will be.
Also we are having a log of sigmoid function basically. So it should be in the range of 0 to 1, and it should not go below 0 or uh like behind 0. Are you understanding?
See.
Yeah, this thing only I'm saying, yes.
Yeah. See, consider this as some constant value. Ultimately, it will give you some constant value between 0 and 1. Correct? What is h of
Yes,
theta x? It will be some value between 0 and 1. So what you are
yes,
taking? You are taking log of something between 0 and 1.
right.
Any value, any constant value between 0 and 1. So if you have a doubt, what you can do, just again, write a code and just iterate over various values of 0 and 1 and see what is the shape that you will get. You will get this shape. Okay, so all of this is already done. You will get it. So if you have a doubt, write an Excel file. In Excel, simple. If you don't know, want to write a Python code or something, in Excel, take 0, 0.1, 0.2, 0.3, up to 1, take say 50 points. And then take a logarithm of that point, I mean minus logarithm of that point, and see what will be the curve of that function. It will be this function.
Yeah, but in linear regression, we have a ball-shaped curve, right? Here we don't have a complete ball-shaped curve.
It is
That is,
complete ball shape because this was only for a one class. This is for only one class. For the zero class, we have, sorry, this is for the zero class. Sorry, this is for the one class. This is for the zero class ball shape. We are combining together. We have, see, our cost function originally we defined for both the classes separately. But I cannot do optimization when I have this kind of a function. So what I will do, I have combined them together. This become the cost function. So, okay, this is for the class 1 and this is for the class 0. So this is for the class 1 blue curve, class 0. We are adding them together. So we got a bowl shape.
okay. And
Right.
and yeah, below the ball shape also we are having some of the curves. So those are
That's
what
okay.
like what we
That's
can say
okay.
about them. Yeah.
That's okay. That's okay. Because we are interested into more generalization performance. This way during training, we try to achieve the minimum of minimum of the cost on the training data. Still, we may not reach to this zero cost. We
Yeah,
also don't
okay,
want to
that's
reach
good.
to the zero cost. Why we don't want to go to the zero cost? What will happen? We have discussed that also.
Overfitting.
Overfitting. So that is okay completely. So in practical scenario, this will work well and will give us a good generalization performance. Even if we are not reaching to cos 0, we don't want to reach to the cos 0 on the training data set. I should use the word,
Yeah,
right?
and ma'am, like I haven't get the answer to my question of
What?
if we have more than two classes, like that curve will be very complex then.
Aman, I have not completed my discussion yet.
Okay, okay, fine. Yeah, I thought we are at the end of the class, so that's why I asked.
Next slide is
Ma'am,
for your
just
answer.
Okay.
Yeah.
yeah, ma'am, just a small query from my side. Since here we were not having the complete convex curve, so that is
Hmm.
the reason we have like done the scaling on the hypothesis
No,
to
no, no, no.
make
1
it
minute.
convex.
1 minute. We have a convex curve. You said we do not have a convex curve. We
No,
have
no,
a convex curve.
finally we are getting, but
Huh.
initially since it was not there, that is the reason we have taken the log, like and done the
No, no,
scaling
no.
of the
1 minute.
hypothesis
1
function.
minute. See your initial. What do you mean by initial? See here, just a comparison. Which cost function I should use? There's no initial point over here. Okay, the decision. I mean, you should frame it your question such that which cost function I should use. Can I use a mean square error cost function over here? Then what happens? That is what is the correct question. So if we cannot use a mean square error because we are not getting a convex form. If you ever got a doubt, again take an Excel, use that, and you will get a non-convex chart. So if we are not using a mean square error, we can use something called a cross entropy function. This is a cross entropy function. Okay. Now, how the cross entropy function can give us a convex function? For that, we have this is how I started. Let's divide it for the class 0. What is the curve? For class 1, what is the curve? But we are combining that becomes our cross entropy. We cannot have a cost function for different classes, right? So this is just for explanation that yes, this is a log, and we combine them. When we combine both the log curves, it is actually becoming a convex curve. So it's our initial point. We started why we cannot use MSE for the as the cost function for a logistic regression.
Okay. What is the meaning of cross entropy here?
It's a theory of entropy. I'll not go in
Yeah.
detail of that. It's known as that's your question is very valid. So cross and entropy. Entropy, it's related to information theory. So it's a lot of theory behind it.
Just one liner, if you can just.
It's
tell us.
about we are talking about two different classes, and we are finding out this is an error function. We are using it as an error function. So if a point belong to class 1 and we are classifying it as a class 0. So basically that see, one liner cannot be explained with any concept. That is, half information is, it's a negative information actually. So if you again, entropy concept, I'll touch upon briefly on a decision tree, because there also we'll come back to entropy. Entropy, not the cross entropy. Okay. But again, these all are your homework points. You want to know more detail on cross entropy, learn. Lot of resources are available. Can I go ahead with the multi-class? It's not difficult. Multi-class, let me complete. Amani is also asking since when about multi-class. Yes. Not getting any answer. Multi-class is a theory. There's no maths in that.
Yes, ma'am. Please go ahead.
Now, logistic regression can give us only a linear decision boundary. That means if I go back to a decision boundary over here, this linear decision boundary, it can only divide between two classes, correct? Something which is above the line, something which is below the line. I cannot use logistic regression for the multi-class classification as it is. But yes, we have a way around over here, how we can use it. So multi-class, this is a multi-class classification. I have 3 classes. This is an example of binary classification, and this is example of multi-class classification, where I have to have a 2 decision boundary for 3 different class information. So there's something called one versus all. I'll directly go come here. What we will do, first one class. Sorry, I'll not draw the line. I'll not draw the circle. 1 minute. So this is triangle versus rest of the data points will give us say one model, which will one hypothesis 1 will give me class 1 versus all. The second model will give me class 2 versus all. The third model will give me class 3 versus all. So likewise, I'll have 3 different classes, and whose posterior, suppose now I want to find out the class information, wherever the posterior probability is high. So say here, I'll write down this in the form of a probabilistic equation. Probability y is equal to 1, given our input and the theta. The second model, the hypothesis function, that means probability y equal to class 2, given input features and the parameters. And third is probability y equal to class 3, given input features and the parameters. Now here, if this probability will be high, which class it will be? In this case, it is triangle. In the second case, if this probability will be high, that means in the second case, it will be say square. In the third model, if this probability would be high, then it will be cross. Okay, in individual model. Now, for the final classification, I can say if this probability is high, or this probability is high, or this probability high. Out of this 3 class probability, which one is high, that will become my final class probability. This is how we will find out, we will solve the problem of multi-class classification using logistic regression. Approach is one versus all.
Is it a
So-
naive base?
It's not a naive base. It's a technique. There's no algorithm. Because you still want to use a logistic regression for a multi-class classification, this is how we can use it. So this is a theoretical. Train a logistic classifier for each class to predict the probability of that class, like this 1, 2, and 3. We will do it 3 times. Then given a new input, pick the class I that maximizes this posterior probability. So here I've got a this 3 probabilities, and will get the maximum probability. So it's a kind of algorithmic technique rather than another algorithm, a hack or a way around to use to overcome the drawback of logistic regression. But in practice, there are other multi-class classification algorithm which can be used, like decision tree or decision tree, or neural network, like that, or the ensemble techniques. So what we have learned logistic regression. This is the model or a hypothesis function. Then we have learned what is the cost cross entropy cross function. For the hypothesis, it is a sigmoid function. Then we can use a gradient update rule. It's the same gradient update rule, nothing different. And during the inference, like we have done, or the learning, the learned parameters that we will use to perform the prediction on the unseen data set. So for that, again, we will use the hypothesis function. This is what we have learned. Okay, this is an example of sentiment. Okay. 2 example, what I'll suggest, if you can go through it, that would be better. Next class, you can ask me the question of this 2 example. I suggest you solve with pen and paper and first verify the answers if they're coming wrong or right, and just do start from start to end. That will help you in your exam. You have only 2 weeks remaining. So both of this example, please do. I mean, I'm not telling the similar kind of problems will come, but to understand the concept from start to end, it will help you. Okay, and then concept overfitting, underfitting. This I can take in the next class. It is just 5 minutes, nothing more different. You want me to complete today or next class?
Next class.
Next class.
Okay,
Next class, ma'am.
fine, fine. But I suggest strongly, please solve this 2 example. You got a time today. Your next class is in the evening.
And there is a quiz today.
Acha, for which?
ISM.
ISM, okay.
Today
Fine.
and tomorrow. Yeah.
Yeah.
Would you be giving some question bank type of things which can
No.
help us in exam? No.
No question bank, but you will get the final year paper and see maybe one more semester paper. We will discuss one paper in the class, last class, and maybe final semester paper is up. You already know that. You already have it, right? One will upload it. I think it's not uploaded on Takshila. Will upload it. The other things are uploaded on Takshila, right? Quiz dates and assignment dates are there. Then your labware are assigned. All those things are done.
Yeah.
Yes, ma'am.
Okay. We'll discuss one paper. Some sample paper we'll discuss.
Ma'am,
Some sample questions.
for lab, we can use our Google Colab also, right? Or do we need to use
Yes.
Labware?
No. Labware is for 1 minute. Labware. Okay. I don't know what you meant by Labware, what you have understood by Labware. That's
Yeah, I
only
might
for
be wrong. Yeah.
An
it's
AWS
only
VM virtual machine.
no. You have got what some lab access also, remote lab access. Huh?
Right.
Huh?
Those are just VMs, like AWS spins up VM. That's it. So
See, Labware is this. You must have got access to all your courses. Like here we have a machine learning where only the examples are given. You can run it. Ready Jupyter notebooks are given. Where I also uploaded the same thing what I uploaded last class. It's here available.
Yeah. So that we can do. Anyways, we can do
Anywhere.
indirectly. Yeah.
But remote lab right now, I mean, you can try get acquainted yourself. This remote lab, basically, we have got very good servers. L40S servers. So it will help you once you get used to of it. Maybe deep learning, it will help you. Right now you
Okay,
can use
okay, got it.
anything, but use that remote lab. You can use Google Colab also. Take very heavy, high lot, what do you call more size data set, bigger data
Okay.
set, and run on the labware for your own understanding. So all of this are available here for your. This is our future engine. This is the feature engineering. Okay.
Mhm.
So all of this are available here.
Sure, ma'am.
Hmm?
Thank you.
Okay.
And ma'am, we are going
Huh.
to discuss the sample paper or like
Yes.
problem statements before midsem exam also, right?
Yes. Yes. Yes.
In one of the class.
Okay. Now one thing. We have 2 sessions remaining. Whatever is remaining from today, I strongly suggest try to solve those 2 problems. You people are not ready to wait extra also. So next class, whatever will be covered based on that, I might take extra class in the last week before the 8th session. So decide whether you want an extra session or you want to stay back extra little if we won't be able to complete.
Stay
Okay, so
back.
by
Stay back.
So how much extra time you need
so yeah,
staying
that's
back?
what.
If we stay back every class, if
Maybe
we start
15
from next class or
only
something.
2 class remaining, maybe 15-20, not more than that. Today also you could have allowed me to complete that part, but it is only
So that
15
will be
minutes.
good because already we have many classes and webinars.
Understood. That's the reason I'm extending it. So you'd make a decision. 2 classes are remaining. Classification evaluation metric probably will take 1 hour depending upon your questions, and decision tree will be over in 2 hours. But then we'll need time also for a discussion of the paper. Right. So let's see next session how much we're able to cover. Try to stay back for the next session. Not difficult. Now, whatever mathematical, heavy mathematics is over, classification metrics is more of intuitive and simple formula where you just have to remember formula, no derivation, nothing. But understand it's more of interpretability purposes. And decision tree is very simple. So if then else rule. Only entropy concept is there, and then how we build a decision tree. Very scoring also, very simple, very powerful algorithm and not so mathematically heavy. So we'll be able to complete. Let's see. So at least be prepared for the next week. We can take some time extra.
Okay,
We
ma'am.
we
Okay.
will have only decision tree or boosting algorithm as well.
No. Only decision tree before midsem. Ensemble will learn post midsem.
Okay.
Boosting everything
Yeah.
post midsem. Yeah.
Thanks.
Yeah, so ma'am, quick request, like the paper the sample paper which we're going to discuss, if you can share it prior to that, we can solve it by ourselves.
That's what
And
is it?
that
Is it done? Yeah, that's what I want. I cannot discuss everything, in
so
1
the
hour.
discussion, so the discussion will be
Yeah.
much fruitful. Like we'll be
Correct.
having,
So it's not
Can you share,
uploaded,
ma'am?
no yet. It's not uploaded, right? On Takshila, can somebody
No,
let
ma'am.
me see? Not
It's not
uploaded. Okay,
uploaded.
yeah. I'll do it by Monday, Tuesday. I'll upload it.
Yeah, please, ma'am. Yeah, sure.
Yeah.
Thank you.
We'll upload the same discussion. No, what we'll do for the rest of the section also. That's the reason. Otherwise, I could have uploaded right now. But let's see.
And one more request, ma'am, like some other teacher in the maths, like they have shared some kind of notes PDF file. It was quite summary of the entire content of the course, right? And which is helping us to summarize all of the concepts in mathematics. If you have similar kind of things in the machine learning, which can help us to summarize the things and can help us to create a mind map, that will be really great because we are working professional and it's really hard to.
Understood, but I don't have. Only the slides are there. Maybe some AI tool can be used to convert that into the notes format. But slides are there, and see. Okay, let me just go back to my courses, and then I have the machine learning. Okay, here, if you look at this slides, okay, these are little more detailed. If I go to introduction to ML for a student reference. So what we are covering in little more detailed things are available. So try to open this slides also. Some examples which are not taken in the class are also part of this. So once go through all of this, and I am changing because I see the pulse of the class and I might change little bit. Like I've added some extra slides here. I know this kind of questions might come. So every time I keep on changing a little bit by looking at the class, anticipating what kind of questions might come. So that is what is my way of teaching. But the general concept and the general topics you will find in this. Like you want something written in the SF format, right? That we don't have it. Maybe maybe I will have to figure out on that to use, because there are a lot of concepts we are discussing. You can use this transcript. Okay, one good way. There are transcripts over here.
Ma'am,
Do
is
you
today's
also get
class over?
access to Yeah, it
Yes,
is over. You
we
can leave. You can leave.
Yeah, okay, thank you.
yeah, ma'am.
Yeah,
Yeah, we can
you
see
have
the
a
transcript. Yeah, while we are seeing the
that's a
recording lecture
summary.
now, then we can
You
access the
can see.
transcript.
So please do. That's a kind of a summary. है ना? That's a
Right, ma'am,
summary, and
that
you can refer the class slides and the transcript both.
Yeah, fine, ma'am. And ma'am, last thing, sorry to ask so many questions here.
No, it's okay.
Last
Class
thing
is
is,
over. Class
yeah,
is over. Yeah.
yeah. So the last thing is, ma'am, like the loss of formula. So in the previous 3 sessions, they were heavily math. So I was just trying to mug up the formulas, but I'm just feeling lots of difficulties while applying those formulas in order to solve the problem. If we take about the gradient descent, right? So I'm like not able to figure it out while reading the problem statement that how to apply gradient descent formula or the least square method.
We have done no one
Fit-
problem on that.
Ma'am, that is not like suffice. I think just one problem of that particular
How
implement the
many problems
things.
you want? But that problem
At
is end.
least
That's why I always tell. Did you try with pen and paper that problem? So right from that's
yes,
why the problems are there.
yeah, I tried it. But anyways, ma'am, I will try it
What's
again.
the problem? So you have to identify
Uh,
what's the problem. Yeah.
the problem is to like read out the question and then fitting it to the like it's very hard to solve the mathematical equation because we are touching the like these things after 10 or 15 years, so feeling some hiccups while solving the problems.
Yes, I know, but this is very exhaustive syllabus. So this is what speed which we can do. We can go. But yeah, at least one problem if you solve end to end with pen and paper, with Excel, you will come to know what is happening, where will things will fit in. So tomorrow, next class, again, I am telling you, I know that you people will not come with at least, look at those problems. We'll see these two problems, so you will come to know.
Yeah, that will be
Two
really
problem will
great,
come
ma'am.
to
At
know.
least,
But
yeah,
see,
at
all
least we can
detailed
solve it.
steps are not written. That you have to calculate. We'll not write all detailed steps. Otherwise, you will not calculate anything. And what will you do in the exam? So detailed steps are not mentioned, but I'll tell you. So likewise, similar way, it is done in linear regression also. Machine learning is going to be difficult it is going to be difficult, but trust me, second semester is going to be very easy. Because lot of concepts are clear and deep learning will only focus on the deep learning. You can ask your seniors how difficult the second semester is compared to first semester. So hang on for the
Only
first
this
semester.
subject, yeah. Out of 4 subjects, like not sure about what others, but I'm like mainly facing the issues with the machine learning concepts.
Machine
Other
learning.
subjects are fine, like just ISM or the ACI or the mathematics. Those are quite okay. Like we will be able to pop up the things by end of the semester. Yeah. But anyways, we will put some extra efforts in it now.
Okay, you're
Yeah, thank
finding
you
it
so much.
This is
difficult.
like
Yeah, please.
slabware option is not coming.
Yeah,
Yes,
even
yes,
I don't know why.
that's what
I
I
don't
was about
know
to
because
say.
we have received I have received an email last Saturday only. I've asked them, okay, labware access is given. You all must have received the email also because I was only in there was some
They,
Takshila announcement or something was there. I received an email.
yes, we do have received the email, but they have
uh,
provided the access to lab via where we
hmm.
can spin up the VMs, like we can connect to the VMs.
Oh,
So that is the
labware is
access
not
they have.
accessed.
So they have not provided the access to labware where these Python notebooks are there. I was
Oh,
trying to find out the
okay.
same. It
Okay,
is still
okay.
not there.
I'll write back to them again. Yeah, I thought labware access is provided. Okay. I'll write back to them. I'll write operation.
Ma'am, regarding the books, ma'am, just a reminder.
So this is, see, I won't suggest you do this as your first reading book. Stick to Tom Michel and Christopher Bishop and our slides. That's what I will say. And the references that we give in the end. Like here, always I've mentioned the references. Stick to those references. Okay, that's all. But for the extra understanding, like whenever after the you have got any time, this is a nice book to understand the probabilistic aspects of machine learning. Okay.
One more book just above, ma'am.
Which book? That's Thomas Mitchell. Yeah, it's a Tom Mitchell, not Thomas. Yeah, Tom Mitchell. Yeah, same one I said, no, Tom Mitchell book.
Okay, ma'am. Thank you.
Yeah, all PDF are available. Yeah. Okay. Anything else? I'll just stop recording. Thank you.